Hello, my name is Nicholas Stewart, and this is my demo video for Experiment 10. First, I'm going to construct figure 10-1, which includes an XOR gate and an AND gate. Before I do anything, I need to set up my breadboard correctly. One moment, please. Okay, so I need to connect my ground to my breadboard and power to my breadboard. First, I'm connecting my ground. Next, I'm connecting power. Now I'm going to make sure my ground and my power are connected to both the top of my breadboard and the bottom of my breadboard. Okay, now I'm going to need chip 7486 and chip 7408. Here's chip 7486. I'm placing it in the middle of my breadboard. And the AND gate chip, chip 7408. Next, I need to make sure that both chips are receiving power. And that both chips are receiving ground. For chip 7486, power is pin number 14. So here is pin number 14, and I'm connecting that to power. ground is pin number 7. So I'm connecting pin number 7 to ground. Next, I'm going to connect my AND gate chip to power and to ground. So my AND gate chip, like chip number 7486, has power at pin number 14. And ground is at pin number 7. Okay, both chips have been wired to ground and to power. Next, I need to make sure that I'm forming the proper connections between the chips. Let me turn back to my experiment page. Here we go. Okay, so I need to connect the input, the first input of my EX-OR gate to the first input of my AND gate. And that will be input A. That together will form input A. So now let me look at my diagram for an EX-OR gate. Pin number 1 is input number 1 to the EX-OR gate. So I need to connect pin number 1 of chip 7486 to pin number 1 of chip 7408 of the AND gate chip. So here we go. I'm connecting pin number 1 of chip 7486 to pin number 1 of the AND gate chip. Next, I need to make sure that I have the second input of my XOR gate connected to the second input of my AND gate. The second input is pin number 2. I need to connect pin number 2 of my XOR gate to pin number 2 of my AND gate. And that will form input B. So let me find 1, 2. 1, 2. Okay. Next, I'm going to connect the inputs to to toggle switches. The inputs are going to be connected to toggle switches. Excuse me. So, input A, that's pin number 1. Is going to be connected to switch number 1. And input B, pin number 2, is going to be connected to switch number 2. Next, I need to connect my sum and my carry. I need to connect my sum and my carry to LEDs. So my sum is going to be pin number 3 of my XOR gate. And that's going to go to LED 0. My carry output is going to be pin number 3 of my AND gate chip. And that's going to go to LED 1. Now that the circuit is complete, I'm going to test the circuit. When input A is 0 and input B is 0, the sum and the carry will be both 0. Let me turn on my power. Okay, for some reason I'm getting a carry of 1. I have to find out what's wrong with my circuit. Okay, I think I found out what the problem was. I was using a NAND gate chip instead of an AND gate chip. So I replaced the NAND gate chip with an AND gate chip. And now the circuit appears to be working correctly. So, when A and B are both 0, then the sum and the carry will both be 0. As you can see, A and B are both 0. And also the sum and the carry are both 0. When A is 0 and B is 1, the sum is 1 and the carry will be 0. When A is 0 and B is 1, the sum is 1 and the carry is 0. This is because in binary, 1 plus 0 is 1, with no carry. Now let's look at the opposite. A is high and B is low. But still, it's 1 plus 0 in binary, which is 1 with no carry. Next, we have A as 1 and B as 1. In this case, 1 plus 1 in binary equals 0, 1. Sorry, it equals 0 with the carry of 1. So, sum is 0 and carry is 1. Sum is 0, carry is 1. And that's it for this circuit. Okay, next we're going to design figure 10-2. Oh, before that, I forgot to mention that, as you can see, circuit 10, figure 10-1 behaves as a half adder. A half adder. So that's why it was able to add these binary numbers together to create sums and carries. Next, we're going to create a full adder. I'll need D flip-flops, 1, 2, 3, 4 D flip-flops, 1 4-bit parallel adder, and 4 EX OR gates. So I'm going to need chip 7483, which is my 4-bit parallel adder. Here it is. Let me place chip 7483 in the middle of my breadboard. Making sure that the half circle is on the left. Next, I need to place 2 D flip-flop chips. My D flip-flop chips are chip 7474. So I'm going to need 2 of those chips because each chip contains 2 D flip-flops. Here's 1. And 2. Okay, next I'm going to need my EX OR gate chips. My EX OR gate chips, actually I only need 1 chip because 1 chip contains a bunch of them. So here's my chip 7486, although it's hard to see. Okay. Next, I need to add power and ground to each chip. chip 7483. Let me check to see what chip 7483 needs to be connected with. I mean, how chip 7483 is connected to power and ground. So ground is pin number 12. Sixteen, 15, 14, 13, 12 gets connected to ground. And power is pin number 5. One, 2, 3, 4, 5 gets connected to power. Okay, chip 7474. Power is pin number 14 and ground is pin number 7. Power is pin number 14. And ground is pin number 7. Again, power is pin number 14. And ground is pin number 7. Chip 7486. Power is pin number 13. Oh, sorry. Ground is pin number 13. Sixteen, 15, 14, 13 goes to ground. And power goes to pin number 5. One, 2, 3, 4, 5. Oh, hold on. 1, 2, 3, 4, 5. Something seems wrong. Let me make sure I have the correct chip. No, I'm looking at 7.6. I need 8.6. That's why. So let's find 8.6. Power is pin number 14 and ground is pin number 7. where's pin number 14? And ground is pin number 7. Okay, next, so all of my chips are connected to power and to ground. Next, I need to form the connections between them. Okay, so Q, the output Qs of my D flip-flops. Well, first of all, let me handle the clocks. The clock inputs of my D flip-flops need to be connected together and then connected to the clock output on the trainer. So, let's look and find out what clock is on the D flip-flops. On the D flip-flops, clock 1 is pin number 3, and clock 2 is pin number 11. So I need to connect pin number 3, 1, 2, 3, to pin number 11. That's 8, 9, 10, 11. Oh, hold on. I'm dealing with this one first. 8, 9, 10, 11. Next, let me do the same thing to the clocks on this one. Pin number 3 gets connected to pin number 3 gets connected to pin number 11. Next, I need to form a connection to the clocks. Not a connection to the clocks, but a connection between the clocks. So, pin number 3 on this one is going to be connected to pin number 11 on this one. Now, I need to connect all the clocks need to be connected to the clock on the trainer. There we go. Next, the D inputs need to be connected to the sigma outputs of the 4-bit parallel adder. So sigma 1 of the parallel adder is pin number 9. And that's going to be connected to Q number 1. That's pin number 5. Seven, 6, 5. Sigma 2 is pin number 6. And it's going to be connected to Q2. Which is pin number 9. Sigma 3 is pin number 2. And that's going to be connected to Q number 1 of the third flip-flop. Of the second flip-flop chip. Of the second D flip-flop chip. That's pin number 5 of that chip. And finally, sigma number 4 is pin number 15. Pin number 15 is going to be connected to pin number 9 of the second D flip-flop chip. Okay, all of my sigma outputs are going to my D inputs. Okay, so next I need to make sure that all of my presets and clears of my D flip-flops are connected to power. They don't appear on this diagram, but these particular flip-flop chips actually do have preset and clear inputs. So I need to make sure those inputs are receiving power so that they receive an input of high, and that way they will be shut down and will not interfere with the circuit. So, for the first D flip-flop, preset 1 is pin number 4. One, two, three, 4. is connected to power. Okay. Preset number 2 is pin number 10. Preset number 2 has been connected to power. Now I need clear number 1 is pin number 1. Clear number 1 needs to be connected to power. And clear number 2 is pin number 13. That needs to be connected to power too. Okay, next I need to connect preset number 1 of the second D flip-flop chip to power. That's pin number 4. Preset number 2 is pin number 10. Sorry about the blurry screen. Okay. Preset number 2 has been plugged into power. Now I need clear number 1 and clear number 2 to be connected to power. Clear number 1 is pin number 1. And clear number 2 is pin number 13. Okay, so all of my presets and clears have been wired to power. Next, I need to make sure that all of the A outputs of my 4-bit parallel adder are going to all of the Q inputs of my D flip-flop chips. Okay, so A4 is going to go to Q2 of the second. Let's do it in this order. A1, the first A, is going to go to the first Q of the first D flip-flop chip. So A1 is pin number 10. And that's going to connect to Q1, which is pin number 5. A2 is pin number 8. And that is going to connect to pin number 9. Pin number 9. A3 is pin number 3. And that is going to connect to pin number 5 of the second D flip-flop chip. A number 4 is pin number 1. And that is going to connect to pin number 9 of the second D flip-flop chip. Uh-oh. There we go. Next, we have connected all of our Q inputs to our A outputs. Next, I need to connect my X OR gates to my B inputs. Oh, I think I said... Yeah, okay. So I need to connect my X OR gates to my B inputs. I've already connected my Q outputs to my A inputs. So let's get started. Pin number 3 pin number 3 of my XOR gate chip is going to connect to pin number 10 of my 4-bit adder chip. Actually, it needs to be going to B1, which is pin number 11. Next, pin number 6 needs to go to pin number 7. Pin number 11 needs to go to pin number 4. And finally, pin number 8 needs to go to B4, which is pin number 16. Okay. Next, I need to connect the second inputs of my XOR gates and my first carry of my 4-bit parallel adder. My carry input of my parallel adder needs to all be connected together and then connected to a switch. Which will carry out the add and subtract, which will tell the which will tell our adder whether to add or subtract. Okay. I need to form a connection from switch number 1 to one of these columns here. Then I need to... That means that every square in this column is going to be receiving the signal from the switch. So now I can connect from the chip to this column so that every input that I connect to this column is going to receive the signal from the chip. So pin number 2 is going to connect to the column first. Followed by pin number 5. Followed by pin number 6. Followed by pin number 12. Followed by pin number 9. And then I need to connect my carry input to one of these in order to make sure that it still is receiving the switch signal. So let me connect it to this one. And the carry input is pin number 13. Okay. Next, I'm going to connect each of my Sigma outputs and my carry output to LEDs respectively. Sigma 1 is pin number 9. That's going to go to LED 0. Sigma 2 is pin number 6. That's going to go to LED number 1. Sigma 3 is pin number 2. That's going to go to switch number no, sorry, LED number 2. Sigma 4 is pin number 15. That's going to go to LED number 3. And now my carry output is pin number 14. That's going to go to LED number 4. Okay. And my circuit is not working, so I need to find out why. Okay, I at least got it to work a bit better than it was before. So now, as you can see, it's counting down in binary. Because each time it subtracts 1. Then if I flip it the other way, it starts adding in binary. Adding 1 each time, according to the clock. And that's all for experiment number 10. Thank you for watching.